In this module, we'll look at thermodynamics of simple fluids. We are often interested in the state of matter. Is there ice on the sidewalk or on the roads, or has it melted into water? Is there water or ice in our waterways that our ships use? Is it a liquid or vapor state running through our turbines or refrigerators? Is there liquid, vapor, or solid in the pipelines that we use in factories? When we process materials, metals, composites, polymers, oils, are they in their liquid state, their vapor state, or their solid state? How do the states change when we add different additives or when impurities come into the system? Accurate knowledge affects the design of materials, efficiency of processing, and even safety in and around plants. That's the reason we are interested in state of matter. There are various ways for us to understand the state of matter and to analyze them. The analysis could be based on graphs, on equations, on correlations of different kinds. As any matter absorbs or loses energy, its state changes. It could change its phase, its density, pressure, internal energy, and even its ability to absorb energy could change. As the properties change, their usefulness changes, and we need to account for these changes when we design processes or instruments to deal with them. Hence, we need to know a priori, beforehand, how a material will behave when energy is added or removed. Various models of increasing complexity are used to describe or predict this behavior. Good models are ones that describe the behavior of a material better. Usually models that replicate the internal interactions of a fluid are better in predicting their properties. There are many ways we can understand material. We could use graphs or pictures to depict the state of materials. We could use equations that predict their behavior. These equations could be based on first principle understanding of how the molecules interact, or they could be based on correlations from experimental data. We will look at all of these methods and understand their advantages and disadvantages. We can use graphs to understand the state of materials. We know that any pure material can be described by its density or specific volume at a given pressure and temperature. So we could use a pressure-temperature diagram to understand the conditions in which the material exists as a solid, as a liquid, or as a gas. This diagram would also help us understand the regions or the conditions when the solid transforms into liquid and when solid and liquid both coexist. Similarly, this graph could help us understand where liquid transforms into vapor or when liquid and vapor both coexist, and so on for solid and vapor. For example, this is a pressure-temperature diagram for water. This region here is the region where water exists in its solid phase as ice. This region is where it exists as a liquid phase, water. This is the vapor region. This line here is the solid-liquid fusion curve. It represents all the points that describe the state or the condition when ice converts into water. So these points on a pressure-temperature diagram, P1, T1, P2, T2, and so on, are the only points where solid ice will convert into water. There is no other point in a pressure-temperature representation where solid ice will convert into liquid water. Thus, this line connecting all of these points represents the transformation of ice into water. Thus, if I had a certain pressure, I could find out what the temperature would be for transformation of ice into water. Similarly, if I had a certain temperature, T, I could find out the pressure at which ice will transform into water. Similarly, this line here is the line that goes through every point on this pressure temperature diagram where water will convert into ice. These are the only points defined by P3 and T3 or P4 and T4 and so on where water will convert into vapor. Thus, if I had a certain pressure, I could find out the unique temperature for that pressure where water will become vapor. This line here is similarly the locus of all points in this diagram where solid ice will sublimate into vapor directly. So for a given pressure, I could find out the temperature at which ice will become vapor. Another thing that this graph tells us is the condition under which ice will transform into water or ice will transform into vapor. So for example, I would know from this graph that at this pressure, ice will not sublimate. I can know from this graph that only at pressures below this point, ice will sublimate. So this is the vapor-liquid vaporization curve, and this is the solid vapor sublimation curve. This point here is the triple point. This is the only point on this graph where solid, liquid, and vapor coexist. There is no other point. This point here characterizes this material. In fact, the purity of water can be tested by looking at the triple point. Pure water will always have this triple point. This specific pressure and temperature is the only point where solid, liquid, and vapor will coexist. Another point on this graph is this critical point. We said that this line is the locus of all the points where liquid water will transform into vapor. However, this line ends here. What that means is there is no point beyond this where liquid water will actually phase transform into vapor. At points beyond this point, which is called the critical point, the last point on this curve, at points beyond this there will be no phase transformation. In fact, beyond this point, it is not possible to differentiate between liquid phase and vapor phase, and hence this region is called the supercritical region.